Hello, and welcome back to CS422 Theory of Computation. Today, we're going to recall what we talked about last time, and we're going to extend it. So let me show you the slides. Last time, we talked about two applications of the reachability method. So let me recall for your benefit. The reachability method is a way of looking at the execution of an algorithm as a path in a directed graph. In this directed graph, every node corresponds to a configuration of that algorithm that is in our perspective configuration of a while plus program, where configuration means kind of a snapshot recording all the states, the values of all variables and the program counter. And if the underlying algorithm runs in polynomial space, then that means that every node in this graph can be described using a polynomial number of bits. The graph in itself will in generally have size exponential, will have an exponential number of such nodes, right? So we cannot afford to even store this graph, but the reachability method is generally speaking a way of keeping that graph implicit in our conception and then devising memory efficient algorithms that operate on this graph. And if the underlying algorithm is a deterministic one, that means that every node, every configuration has a unique successor unless it's the end configuration when the algorithm has stopped. There's also a start configuration that includes the argument, the data with which the algorithm is executed. So when we execute the same algorithm with a different input, then the resulting configuration graph will generally look different. If the underlying algorithm, however, is a non-deterministic one, if you can make guesses, a guess while plus program, then it means that a node configuration may have several, actually two possible successor nodes, depending on whether the guessed value, the bit guessed, is 0 or 1, then that corresponds to two possible successor nodes. And we've used the reachability method in order to prove that quantified Boolean formula is p-space complete. Then we will first take an arbitrary polynomial space algorithm, then consider the reachability graph, and then expressed reachability in this graph from start to end configuration recursively as Boolean formula with both existential and universal quantifiers, so that the Boolean formula in the end has only polynomial length and thus can be computed and output in polynomial time, and this would constitute the polynomial time reduction from any master reduction from any polynomial space algorithm to quantified Boolean formula. That was our first example of the reachability method. And then we consider the second example of the reachability method, namely Savitch theorem. So let me recall what is the statement and the proof of Savitch theorem. For Savitch theorem, to state it in its full generality, we consider a more general refined complexity notions. So previously we would consider polynomial time computation, non-deterministic polynomial time computation, and polynomial memory computation. Now we want to look more closely and look at time t computation, where t is here in a general function, non-decreasing function from natural numbers to natural numbers. That means, oh, hide that right here. You see that function. We say that a decision problem is solvable, is decidable in time t of n, if there exists a wild program which decides that using a number t of n steps for every input of binary length n. And similarly, we define n time, non-deterministic time, so that meaning that there exists a non-deterministic wild program which accepts this decision problem in at most t of n steps for n denoting the binary length of the input, regardless of the guesses. So the time bound t of n must hold for every possible sequence of guesses of the algorithm. And similarly, space t or space f means that the algorithm uses at most f on n bits of memory during the computation for every input of length, binary length n. And similarly, non-deterministic space, meaning non-deterministic while plus program running in that amount of memory, regardless of the non-deterministic guesses. And so this is the generalization, a tightening stratification. For example, polynomial time means that t can be any polynomial, and polynomial space means that this can be any polynomial. And now we can state the Savitch theorem, which says that for every such time or memory bound, when there exists a non-deterministic while plus program running in that amount of memory, then there also exists a deterministic while plus program running at most quadratically more amount of memory. So that in particular, when we replace t to be any polynomial, it means that NP space is the same as deterministic P space, right? So because, well, deterministic P space, of course, is contained in non-deterministic P space. Non-determinism is only more powerful, and conversely, non-deterministic space can be simulated, can be also executed in deterministic space with at most quadratic overhead. And when the original overhead is a polynomial, then the quadratic, the square of that polynomial is again a polynomial, so that n non-deterministic polynomial space is the same as deterministic polynomial space. Now you see here that the term every function t from n to n is put in quotes, and there's a reason for that, because of course it will turn out in the proof that we'll need to be able to compute that function itself, and computing that function also incurs some memory consumption, right? Now it takes some advanced diagonalization to construct functions which require a lot of memory, more memory than the function itself has value. And so there's actually a technical condition underlying these quotes, namely the function must be what is called space constructible. Computing the function must be possible in an amount of memory that is roughly bounded by the function value itself. But this is our, we'll return that once we've completed the proof. For now, let's just ignore that condition and look at the general proof idea. So according to the theorem, we have to start with a non-deterministic while plus program, let's call it A, that accepts the decision problem L using amount of memory, which we'll abbreviate here with S. And remember that accept means, for non-deterministic computation, it means that for every input in L, there must exist a sequence of guesses of the non-deterministic while plus program, which leads the program to accept. Whereas for every input which does not belong to L, any possible such sequence of guesses must result in the algorithm to reject. And the emphasis here is this, remember this asymmetry. In order to accept means there must exist a sequence of guesses. It's not about how to find that. It's not about random guesses. It just says there must exist a sequence of guesses. And remember, this is our semantical conception of non-deterministic computation. The syntactical conception is the witness perspective. There exists something, but here we don't have a theorem like we had for NP, where we had this syntactic characterization of NP, that there exists polynomial time size and polynomial time verifiable witnesses. This is not the case here for non-deterministic memory bounded computation. And this is exhibited by the theorem of Waldo-Sedgwick that we currently have started to prove. So let us look at such a non-deterministic computation and apply the reachability method here a second time by encoding configurations of the algorithm of the wildpath program in bits. But now, since it's a non-deterministic computation, it means that the configuration graph here may have nodes may have several successors. Also, let me emphasize again that the configuration graph in general need not be connected. There may be configurations which will never be reached during computation. And the essence here is really to express and to decide whether it's possible to get from the starting configuration, unique starting configuration, to the unique accepting end configuration. Going to explain why we can make this unique using some path. And now the path may not even be unique because it's a non-deterministic computation. So why can we, why is the starting configuration unique? The starting configuration encodes all the variables being initialized to 0. That's unique. And also the input is stored in the dedicated variable x1. And the end configuration in general may not be unique. Right, there are various ways the variables could, various values that the variables could have when the non-deterministic wildclass program reaches its end instruction. But we're going to apply a certain easy transformation to this non-deterministic wildclass program. Namely, we're going to add the instructions that reset, that reinitialize all the variables to 0 right before the end instruction. So right before the end instructions, imagine that there's a block of assignments, namely set the variable x1 to 0, set variable x2 to 0, and so on, so that when the algorithm reaches the end instruction, all the variables have the same value 0, and thus in particular the end configuration is now unique after this transformation. So we can really rephrase, using the reachability method, the question of whether the algorithm accepts an input or not as equivalent as whether there's a path from the unique starting to the unique end configuration, whether there exists a path, but the path, let me emphasize also that again, itself may not necessarily be unique. So this is a graph, a directed graph, with U as the start configuration, including encoding the input X, and W is the unique accepting end configuration. And here you see such a picture, an example of such a graph, and it also illustrates the non-determinism, namely, for example, this configuration now has 2 successor configuration. This one has 2 successor configuration. This one has only 1 successor configuration, so it's not a guess instruction. Only the guess instruction induced the non-determinism, having possible several successor configuration. Here's the starting configuration, and here's the end configuration. In this case, let's see whether it's possible to get from the starting configuration to the end configuration. Yeah, I guess so. Here's a path. But remember, in general, this configuration graph will have exponentially many nodes, right? And so we cannot store it, but we want to operate it And we're going to devise an algorithm here that operates on this graph implicitly without spelling out or storing the graph. And the idea is pretty similar to the master reduction from p-space to quantified Boolean formula. Namely, we design a predicate, now not necessarily a Boolean predicate, that expresses whether there exists such a path based on the observation that such a path, if it exists, it must have at most exponential length. That's bound on the number of vertices that this graph may have. And also that means that there exists an intermediate vertex which can be reached within half the overall width, and from which the end configuration can be reached in another half of the width of the graph, diameter of the graph. So that means this predicate, we define this predicate to mean that there exists a path from U to W, and such a path exists if and only if there exists a path of our at most exponential length. And if such a path of exponential length exists, that's equivalent to saying that there exists an intermediate vertex which can be reached in at most half the number of steps, and from which the final configuration can be reached also in at most half the number of steps. So here we have this additional integer parameter s, which is kind of the memory used on this possible input, the memory bound according to the non-deterministic p-space algorithm, and reducing proceeding from s to s minus 1 means halving, right? So this is in the exponent 2 to the s. So this is 2 to the s minus 1. This is half. And so here you see in this example, you see this yeah, you see here this intermediate vertex, and when we applied this reachability method for the master reduction to QBF, then we would spell out that or unfold this recursion. First, we try to use it naively, but in each recursive step, the number of occurrences of this predicate would double, thus leading to an exponentially long predicate. And thus, we would instead express this conjunction using existential quantifier, and thus obtain a predicate of at most polynomial length. But that was when we did the master reduction from p-space to QBF. Here, instead, we're going to apply use this observation, this mathematical observation, right? Remember, every efficient algorithm underlies a mathematical insight, and in this case, the insight is used to devise a recursive memory efficient algorithm that makes these two recursive calls. Yeah, so for since we're devising memory efficient algorithm, we don't really care about the running time of the new algorithm. It's only important that it uses at most quadratically more memory. And that's what we're going to do. We're going to reuse memory during both recursive calls, possibly recalculating properties of the graph repeatedly, but this allows us to kind of relinquish and reuse memory to get a memory efficient algorithm. So this is what we see here on the bottom of this slide, namely an implicit, yeah, let's refrain from spelling out this in pseudocode, a recursive algorithm that evaluates this kind of predicate recursively. So how would it do it? It will receive as input the starting configuration, which uses S bits. It would receive as input the end configuration, which also occupies S bits. And it would receive this parameter S. And recall that in order to do that, we need to somehow calculate S. And this is where the assumption enters that the bound function t here can be computed in this amount of memory without exceeding the memory bound. And once this has been calculated, the algorithm will then try all possible intermediate vertices. So this existential quantifier will result in a huge loop of the algorithm trying all possible intermediate vertices, exponentially many, but each intermediate vertex will again have only up to s bits of memory, and thus the counter, the loop, will reuse this amount of memory to enumerate all possible vertices, whether any of them is such an intermediate vertex. So this existential quantifier translates into a loop of exponentially many iterations, but the loop counter is reused, and the loop counter uses only a polynomial number of bits, namely s bits, and then make this first recursive call, which by induction hypothesis also uses s minus 1 quadratically in s minus 1 amount of memory, and then make the second recursive call where it can and will reuse the memory used here. So the two recursive calls will use the same amount of memory, namely s minus 1 squared by induction hypothesis, plus the linear overhead for this and for the arguments, so that memory consumption of this recursive algorithm is basically described by the recurrence. The memory of with parameter s is O of s plus induction memory use with parameter s minus 1, and solving that recurrence leads to a quadratic bound on the number of bits used. So in this algorithm, which I must emphasize here, is a very implicit algorithm, no pseudocode, but it basically implements this mathematical or logical recurrence as a recursive algorithm. This algorithm can be implemented, can be designed in a while-pass program using only a quadratic overhead of memory, and thus a deterministic algorithm. That's the emphasis here, right? So this loop here is a deterministic loop, and so there's no guessing anymore, and thus the non-deterministic algorithm has been simulated, is simulated with a quadratic overhead by a deterministic one, that thus proves the Savitch theorem based on the reachability method. So that's our recap from last time, maybe with a new perspective, a new abstract overhead perspective. And now we want to proceed to another application of the reachability method regarding non-deterministic memory. So the Savitch theorem would relate non-deterministic memory to deterministic memory with a quadratic overhead. And yes. Yeah, that's a great question in the chat. Thank you. How can we decode U and W in the base case of the recursion? Oh, thank you so much. This is an excellent question, right? So what about the base case of the recurrence? The base case of the recurrence is when S is equal to 0 here, right? So when S is positive, we make these recursive calls, but there's indeed a base case that I need to explain. The base case is when S is equal to 0. That means the question, does there exist a path of length at most 2 to the 0 that is of length at most 1 from given vertex to another given vertex? And this is this means, recall our definition of the configuration graph. This means whether the second configuration is a successor configuration to the first configuration. I emphasize that indefinite because it could be not the successor configuration. In general, any node can have up to 2 successor configurations. And in order to determine that, whether W is a successor configuration to U, that's indeed where the underlying algorithm, non-deterministic algorithm comes into account. So in order to determine that, our new deterministic algorithm will look at the underlying algorithm. The initial configuration corresponds to values assigned to the variables and the program counter. And same for the purported successor configuration. And then it will simulate one step of the algorithm, depending on the instruction, whether it's a assignment instruction, an addition instruction, a subtraction instruction, division instruction, all these deterministic, or whether it's a guess instruction. So depending on the instruction, it will kind of simulate that one step of the non-deterministic program symbolically. This is kind of like a symbolic execution, and thus be able to determine whether W is the immediate, namely when S is equal to 0, that means one step, that means immediate successor configuration to U. Thank you to the chat for raising that question and for giving the opportunity to expand on that and explain that. Right, so to iterate here, this is Walter Savitch theorem is about the relation between non-deterministic space and deterministic space with a quadratic overhead. But let's now, so that means from the space perspective, and non-determinism and determinism are at most quadratically related to each other. Now, how about the similar question for space, non-deterministic space, and co-non-deterministic space? Remember that co-non-determinism means the complement, right? And this is where the asymmetry kicks in the definition of non-determinism. Non-determinism asks whether there exists a sequence of guesses that lead to the acceptance. And the complement of that means that for all sequence of guesses leads to the rejection. And this for all quantifier does not really seem feasible to be expressed as an existential quantifier and thus as a non-determinism. So the relation between non-determinism and co-non-determinism is a big open question, almost as big open as the P versus NP problem, because if P is equal to NP, then of course also co-NP is equal to co-P, and co-P is the same as P. Complement of determinism is the same as determinism. So if P is equal to NP, then also the relation between NP and co-NP, they coincide. But how about the case, similar question regarding memory, non-deterministic space and co-non-deterministic space? Well, according to the Savitch theorem, there can be at most a quadratic discrepancy between both. But as we're going to see on the next slide, the Immerman-Szelepscenyi Theorem says that this is not quadratic. Actually, it reduces to linear. There's at most a linear discrepancy between co-non-deterministic space and non-deterministic space. So that from the various pictures, how P and NP and co-NP could be related for the time question, right? This is all about non-deterministic and deterministic time. The similar question for non-deterministic space is much tighter and actually is all basically answered. And that's what we want to show here, the famous Immerman-Szelepscenyi Theorem. So this is again the recap of our definition for the tight, the stratified polynomial time, stratified non-deterministic polynomial time, stratified polynomial space, stratified non-deterministic polynomial space with this parameter function, any non-decreasing function. And the theorem says that, again, here's some technical suitability assumption, which I'm going to return to later. As long as this is even, we can even deal with only logarithmic space, then in this case assumption, non-deterministic space is the same as co-non-deterministic space, the complement, with a up to a linear overhead. And this is the famous Immerman-Szelepscenyi Theorem, which was awarded the Gödel Prize in 1995. So here you see a picture of Neil Immerman. Yeah, there should also be a picture of Szelepscenyi. Yeah, the proof, ingenious proof, is again an interesting application of the reachability method. But now remember, the goal is to somehow express universal quantifiers or negative answers to the unreachability question in terms of positive guesses where they exist, where we can only guess witnesses positively. Right, so one way of looking at non-determinism is that we can make guesses, but we have to verify the guesses. And if we have guessed wrongly, then the algorithm can and should and must reject and abort the computation, because the semantics of non-determinism is that whenever only when there exists a sequence of guesses, then the input is being accepted. So we can kind of safely abort whenever the sequence of guesses has led to an unfavorable state of the algorithm. But we must make sure that there exists a sequence of guesses for positive instances. So here again, we see the configuration graph underlying the reachability method, with U, the initial, and V, the unique accepting configuration. And here I draw such a picture of this graph. Right, so move that away. Right, here you see a picture. This is a unique starting configuration. That's here in bold. This is the unique accepting configuration. And there are many intermediate configurations. There are also configurations which cannot be reached at all during the computation. The graph, remember again, has exponential size, exponential in S. And let's introduce some refined terminology, namely G of M, where G is this directed graph, consists of all configuration that can be reached within at most M steps from the unique starting configuration. So we kind of introduce a distance on this graph. We kind of subdivide it into kind of shells, where each next shell, next level is a better word, are all the configurations that can be reached from the previous one in one additional step, following one additional edge. And the goal here is now to not express reachability deterministically, that was Savitch theorem, but to express unreachability, because that's the co-NP problem, right? So reachability and its complement means unreachability. Is it impossible to reach the unique accepting configuration from the starting configuration? And the algorithm now can and must and should use guesses, right? We want to use to design a non-deterministic O of S algorithm using a linear amount of space in order to decide the unreachability of the co-NP space problem. So how can we do that? And in order to assert that, let us divide the original claim of the theorem into 3 subclaims that we then prove and that gradually together climb up to describe again very implicitly the underlying memory efficient algorithm for non-deterministically deciding unreachability. Right, and this is why was this awarded the Gödel Prize? Because again, intuitively, right? So guessing means there exist guesses, and the complement means that for all guesses something is true, and it seems infeasible to express this universal quantifier as an existential quantifier. If we could do that generally, then it would follow that coNP is equal to NP. But from the memory of space, where we can reuse memory, where we can reuse computation, and where we can kind of discard computation, that was came quite as a surprise to this 25 years ago. So the first observation is pretty easy, namely for each M, the decision problem given M and given a configuration in this implicit configuration graph, each configuration can be stored using O of S bit, can be decided non-deterministically. That's the easy part, right? This is not about unreachability, but this is about reachability. And the proof idea here is pretty simple. Simply guess a path from the start configuration to the given configuration, right? Not all the N configuration, but keep a counter M and always guess the successor configuration, a successor configuration. And the only trick here is, well, M can be, remember, M can be exponential in S. So storing M, M is exponential, but the binary length is at most S. So we can store this counter without worrying about memory. There's again the assumption here that we can compute S within the memory bound S itself. This is what is meant here with suitable. And then repeatedly guess a successor configuration. The only trick necessary here is that we kind of forget the predecessor configuration. So we start with U, guess a possible successor configuration, decrement the counter M, and then we guess, repeat the same step again. We guess a successor configuration, one of at most 2 possible ones, but we forget the predecessor. And why do we forget that deliberately? Because we cannot store all the sequence of intermediate configuration that could be at most M many intermediate configuration. And remember that M will in general be exponential in S. So storing M itself is no problem, the value as an integer, but storing M different configuration will definitely exceed the memory bound. So we only store a constant number of configurations, namely the current configuration and the newly guessed successor configuration. And once the counter has reached 0, we will check whether we have reached the given N configuration, and if so, we accept, and this algorithm thus correctly decides whether a given configuration can be reached within at most M steps. Okay, so the essence here is guess the path from start to the given configuration, making sure that the path has at most M steps, but not storing all the intermediate configuration, instead forgetting in each round, forgetting the previous configuration. And look at that from the deterministic perspective. Why is this not possible deterministically? Because deterministically it could easily result, for example, into a loop, right? Into if the underlying directed graph has a loop, then a deterministic algorithm, when deterministically finding the next configuration, and then the next, and then the next, could result in a loop where it keeps cycling around without ever reaching the the target configuration. This, of course, can also happen with a non-deterministic algorithm, but it doesn't matter because the only thing we need to make sure is that there exists a sequence of guesses, and guesses that lead to such loops are simply not relevant according to the semantics. The semantics saying that when the configuration is reachable, there must be a sequence of guesses, and of course, there exists such a sequence of guesses that avoids the loop, and that's good enough for a non-deterministic algorithm. So this is kind of a first warm-up step. Let me also introduce some terminology about this level of the graph, namely the number of nodes, the number of configurations that are reachable within at most m steps. Let's call that capital N of m. Because our next subclaim in proving the theorem involves that number, namely the hypothesis that this natural number function is computable in non-deterministic space, linear in S. Then also the unreachability within m steps can be decided in non-deterministic space. So this is kind of a where we're heading for, right? We want to decide general unreachability using only positive guesses. And here, this is feasible actually in a more general sense, namely when we apply m to be 2 to the s. What does that mean, 2 to the s? When m is equal to 2 to the s, then g of 2 to the s, that's a set of all configurations that can be reached at all, right? Because if some configuration is reachable, then it is reachable within at most exponentially in s, 2 to the s steps. So what we're really kind of aiming for is g of 2 to the s. And we want to decide unreachability. We want to decide whether vertex is not reachable in g of 2 to the s. And here we kind of assert some intermediate. Then we assert that unreachability is indeed positively, with positive non-determinism, decidable, but under the hypothesis that this function of natural numbers is computable within this non-deterministic space. Now let's look at this function for a moment. How large is n of m? As I said, the configuration graph itself will in general be exponential in S. So also this number will be at most exponential in S, but its binary length is linear in S, right? So the value is exponential, but the binary length is at most linear. And thus storing or outputting that number is no problem to do in that memory bound. That's one first observation. And the second observation is the question, what does that mean to compute a function in non-deterministically, right? So remember we've introduced, formalized, and talked a lot about non-deterministic decision, where non-deterministic decision means there exists a sequence of guesses, right? What for positive instances, and for negative instances, there exists no such sequence of guesses. But this refers to decision problems where there are positive and negative instances, whereas here we're talking about a function problem where the output is not just yes or no. And the subtle part about non-determinism is that there is no, right? There's only yes or give up. And now we're talking about function problem where the output consists of natural numbers. What does that mean? I'll explain that in just a minute, but just to make you aware of this subtlety here. But what I want to first now emphasize is that if we can show that this function is if we can show, this is the hypothesis, if we show, and we're going to show that in the next step, that this function is computable in this amount of memory, then applying that function with m equal to 2 to the s, then it follows that this function is indeed that also the unreachability is decidable with positive guesses. Okay, so this these three steps together prove the theorem. That's the message here. Namely, according to item C, this function is computable in this memory bound. Applying m to m equal 2 to the s means that the number of vertices, the number of configurations that are at all reachable, right? M equal 2 to the s means at all reachable is computable. And according to item B, if this function is computable, then we also can positively verify non-reachability at all, because if some vertex is not reachable within m equal 2 to the s steps, then it's not reachable at all. And this is precisely the claim. The unreachability is decidable with only linear overhead in positively non-deterministic guesses. Right, and now I've promised to raise your awareness of what it means to compute a function non-deterministically, and so I still owe you the explanation for that. And the explanation for that is, well, the definition actually, namely the same paradigm to guess and verify the value. That means we say that an integer function is non-deterministically computable in some time or memory bound if there exists a non-deterministic while plus program which can make guesses, and whenever these guesses lead to an accepting configuration and accepting computation, then the value output must be equal to that f. Let me emphasize that again. So there are possible choices of guesses of the algorithm, and when the algorithm verifies these guesses and chooses to abort the computation, then that doesn't count. Like in the decision variant, it's always allowed for an algorithm to abort a computation when the algorithm realizes that the sequence of guesses leads nowhere, basically. But there must exist a sequence of guesses that lead to the algorithm to output that function. That's the same as we had for the decision problem. There must exist a sequence of guesses that lead to an accepting computation. But we have a third condition, namely that any possible sequence of guesses that lead to the output of a value, they must output the same value, f of x. Okay, that's a subtlety. Right, so otherwise it would be conceivable that a non-deterministic algorithm for one sequence of guesses outputs this number, for another sequence of guesses outputs this number. And this is prohibited here by the definition that I'm explaining here. So whenever the algorithm realizes that the guesses have been unsuitable, unsuccessful, then the algorithm must abort the computation. If it continues and finally outputs something, then it must be the same and the correct value f of f. That's the semantics of a non-deterministic while plus program computing an integer function. This is what we mean here. This integer function, right, it's a single valued function, must be computable in this sense. And together with item B, which uses the same statement here as hypothesis, it follows that the unreachability as a decision problem, as a yes-no problem, is solvable as with positive guesses only. And this is what gave the Gödel Prize to Neil Immerman. Okay, thus having discussed the 3 steps of the proof, let's now establish the 3 steps separately. And I've already indicated the first step A is kind of obvious, with the only subtlety ideas to forget intermediate configuration, always guess just the next configuration, and see whether within that number of steps the target configuration is reachable. And we're going to use that kind of repeatedly as a subroutine when devising the more and more sophisticated algorithms for B and C. And when I talk about subroutine, we also always have to make sure that this subroutine really, we cannot, remember, we cannot switch the result of a subroutine without or we have to be very careful about switching the result of the subroutine, because we cannot simply replace existential with universal quantifiers. We cannot replace guesses with non-guesses. So let's keep that in mind. So let's first move on to the next claim of the proof strategy, item B. So what do we need to do here? We're given as input vertex, a configuration in the implicit configuration graph, and parameter M to see whether and to decide, to guess, to verify that the vertex W is not reachable within M steps. That's the goal, by making positive guesses. And we use the hypothesis that this number is computable within non-deterministically with that space bound. So the first step is to use that hypothesis and to compute that number, which is the number of configurations that are reachable within M steps. And now we want to make sure that the given vertex, that the given configuration W is not among them. But we don't have the configurations, we also only have their number. Also, this number, remember, can be exponential, so we cannot really even enumerate the configurations. We can only enumerate or store a constant number of these configurations. Otherwise, the memory bound will be exceeded. And so here's the ingenious algorithmic trick. The first ingenious algorithmic trick of Neil Immerman, namely, let's first look at the algorithm and then understand it. We initialize a counter, and then we look at each possible configuration in this configuration graph, whether it's reachable or not, any possible configuration W. And for each configuration, we verify that it's different from the given configuration. Now, the given configuration using a linear amount of memory, any possible configuration. So there's a big loop underlying here, exponentially long loop, but the loop counter W prime again uses only linear amount of memory. So we're still good. And comparing the two configurations is also possible by just comparing them bit by bit. And for each such configuration, we guess. This is where the positive guesses of the non-determinism come into play. We guess whether this configuration W prime is reachable within M steps or not. So we guess one bit that says for each, so for the current value of the loop counter W prime, we guess one bit that says W prime is reachable in that number of steps, or the bit 0 says is not reachable. But now we need to, of course, verify that guess. And that's the important and the subtlety here. We can verify whether the bit 1, if the guess was correct, was that it is reachable. We can verify that. This is item A, right? By item A, we if the guess claims that it is reachable, then we're going to increment the counter. So the counter is going to try to count the number of nodes that can be reached within M steps. And at the end, we're going to compare that counter, when we're done, with a given number. And when that counter differs from the number we've computed here, then we know that we've made some mistake. Let me say that again. So the idea underlying this counter is that this counter counts how many configurations we have guessed to be reachable within M steps. And if at the end of this big loop, we're going to compare that counter to the actual given promised number of configuration reachable. And if the two disagree, then we have made a mistake somewhere. We have made an unfortunate guess, and thus we're going to discard and abort this kind of computation. Does that make sense? This is an important but subtle point, right? So this counter will count how many configurations we could verify to be reachable. And if at the end of this loop, this counter differs from the actual number of configurations which we were promised to be computable, then we've made some mistake and we're going to abort. But let's first continue discussing the loop body. So if the guess says this is reachable, we're going to increment the counter, and we need to verify that our guess was correct. Namely, we're going to guess a path from the start configuration to the current configuration represented in the loop counter of at most m steps, using the same method in item A, namely guessing successor configurations and forgetting successor configurations. And if we're able to reach W within that number of steps, then we're good. But if our path guess of such a path fails, maybe ends up in a loop, then we're going to stop and abort this kind of computation, because then obviously it doesn't mean that there is no such path, but it means that our guesses have not been favorable ones, and thus we simply abort the computation. And after n, that's what I mentioned before. At the end of this loop, we're going to check how many vertices we have guessed correctly to be reachable and been able to verify to be reachable within m steps. And if that is less, then we're going to stop and reject and abort. It cannot be larger, right? That observe that counter cannot be larger than m, because m is the number of configuration reachable, and the counter is only incremented and the computation continues only once the reachability has been verified. So the case that c is larger than m cannot happen. Furthermore, if c is equal to m, then it means that all the guesses have been favorable, have been correct. Both the guesses of which vertices are reachable, otherwise we couldn't reach the correct value of the counter, and the verification parts. And now comes the important logical observation. In this case, if all the guesses have been correct, the positive guesses, that means that also the negative guesses, whenever we guess that a vertex is not reachable, must also have been correct. Let that sink for a moment. If all the positive guesses have been correct, which can be verified by that we have reached the correct value of the counter has reached the actual number of reachable vertices, then it means also the guesses where we guess that a vertex is not reachable must also have been correct. So this is where the implicit complementing comes into part. We can only verify positive things, but using the information how many vertices are reachable, we can kind of verify that all our positive guesses have been correct, and thus conclude that also the negative guesses that which vertices are unreachable have also been correct. And that in particularly means that the vertex W, which was part of the input, is indeed also not reachable, right? So if W is reachable, then we cannot remove that from the loop as we did here. Without, then we cannot, if we remove that from the loop, then there's no way for our counter to reach the actual number of vertices if W is reachable. So the only way for this counter to reach the actual value means that W is not reachable. And so in this case, we're going to stop and accept, right? Remember, we're talking about unreachability. So it means accept here means that W is unreachable. So that concludes our description of the algorithm underlying item B, where the basic idea here is repeatedly applying the item A, verifying that some vertex is reachable within m steps with non-deterministic guesses. And whenever it is reachable, verify that and increase the counter. And in the end, check whether the counter has reached given the promised number of reachable configuration. Now it remains to prove with the item C that this function is indeed computable in non-deterministic space. And this is what we're now going to do, and this concludes the proof. And this in turn is going to be even more involved. It employs the ideas we have already discussed in a even more advanced algorithm, and the idea that we can verify whether a vertex is reachable within m steps, and the idea that we can kind of refute the reachability provided that this function is computable. So this is a final slide of our proof of the Immerman-Szelepscenyi Theorem, but it's going to be subtle, so please buckle up and recollect all your attention now. So the underlying idea is to inductively guess and verify. Remember, that's all semantic of non-deterministic function computation. Guess and verify the next value from the previous one. If we can do that with an algorithm that only makes positive guesses, then we can gradually climb from n of 0. Right? What is n of 0? N of 0 is the number of configurations that can be reached within 0 steps. That's 1, right? We know g of 0, we know n of 0, that's the induction start. G of 0 is only the starting configuration, is reachable within 0 steps, and therefore n of 0 is also 1. And then if we can succeed in proceeding from n of m to n of m plus 1, then we can gradually climb up in a loop that has m iterations. Remember, in general, in our application, m will be exponential, but the running time doesn't matter. We're only talking about memory, and we want to get away with only linear overhead in memory, which means we only want to store a constant number of intermediate configurations throughout the computation. So here's the algorithm that computes n of n plus 1 from n of m. And here you see these kind of levels, where this is one level, and the next level includes the vertices that are reachable in one more step. And that's what we want to calculate. And actually, we're going to adjust and generalize the previous principle with the method of the counter, right? So we're going to initialize the counter C prime, which is going to count the number of configurations which we can verify to be reachable within m steps. And then we're going to check our guesses for each possible such configuration. We're going to guess whether it is reachable in m plus 1 steps. Okay, this is the modification. So C prime is going to try to count to n of m plus 1. And we're guessing whether this current configuration is reachable in m plus 1 steps or not. And if the guess claims it is, then we're doing the same again. We're going to increment the counter, and we're going to verify that. We're going to guess a path of length m plus 1 using the same method as before without storing the intermediate configuration. And if that verification succeeds, then that means our guess here was correct. Otherwise, we're going to abort the computation, not reject, but abort. That should be abort. That's what we already did in the proof of item B, right? But now the thing is, we don't have n of m plus 1 at our disposition to verify at the end whether and which of these guesses were correct. We want to compute n of m plus 1. So we need to find some other way of verifying whether the guesses were correct. And maybe specifically when the guess claims that the vertex W prime is not reachable in this number of steps, we're going to have another loop, a nested loop with again a counter C initialized to 0. And this counter will count the number of vertices reachable within m steps. So this is where the hypothesis enters that n of m has been computed and is stored somewhere. And we're going to do the same again. You see that this is now a loop within the loop. Here's an outer loop, and here's an inner loop enumerating all possible configurations. And another guess whether this configuration is reachable within m steps. Okay, and now of course again we need to verify this guess. And if the guess says yes, it is reachable, we're going to verify that. But now the verification will not start from scratch from the start configuration. But when the guess says yes, it is reachable within m steps, then we're going to check whether there exists now an edge from this vertex W that we just guessed to be reachable with m steps to the new vertex W prime, which we're considering here, whether there exists an edge. If there exists an edge, then it means that W prime is reachable in m+1 steps. Let me say that again. The guess says W is reachable within m steps. We verify deterministically whether there exists an edge from W to W prime. That's kind of like the base case of the induction that follows that's feasible by simulating one step of the algorithm, right? This is a configuration. One edge means that this is a direct successor configuration. That's where the simulation of one step happens using a linear amount of memory, not much overhead. And if it is reachable, then we know that by transitivity, W is reachable within m steps. W prime is reachable within one more step. So W prime is reachable in m+1 steps. But our guess says that this is not reachable. We've just guessed that W prime is not reachable. That means we have made an unfavorable guess, and so we're going to stop and abort the computation. However, if there is no such edge, then there's a candidate for W prime to indeed not be reachable. But first we need to verify this guess, namely the guess that W is reachable within m step. And this is what we've done so far. Frequently, we're going to increment that counter and guess a path from start vertex to W of length at most n. And if that fails, then we're going to stop and abort this case. So what has happened so far? When we reach that point, it means that here we have correctly guessed that W is indeed reachable in m steps, and we've verified that, and we've incremented the counter so that at the end of this inner loop, we can check whether all the guesses made in the inner loop have been correct by, again, comparing it, the counter to the actual value, which we suppose to have been correctly computed. And if we have not reached that value, it means we have made a wrong guess on the way in the inner loop. Conversely, if we have guessed correctly everything here, then this counter, we can verify, check that this counter value has reached this number. And that means in particular that also all these guesses have been correct, right? So we've guessed correctly all vertices which are reachable within m step once we get past that safety condition. And we've been verified that the new vertex is not reachable. There's no edge, because otherwise we would have rejected here. So that at the end of this inner loop, if we get past this condition, it means that we have correctly verified that the vertex W prime is not reachable. Yeah, that's a kind of a unreachability as a decision problem. We've correctly verified that this is not reachable. We don't store that information. We cannot afford storing that information. Instead, this is where the counter here comes into account. We have not incremented that counter, and we have been able to verify that we did so correctly, not increment the counter C prime of vertices reachable within m+1 steps, because we've just verified that W prime is not reachable in that number of steps. So that at the end, the counter C prime it has been incremented. So this is where the positive guesses and the negative guesses where the counter has not been incremented, C prime, also have been verified correctly, so that at the end, the counter C prime indeed contains the number of vertices that can be reached within m+1 steps. This is the end of the Immerman-Szelepscenyi algorithm and proof. So let me take the remaining few minutes to give an abstract overview of this algorithm. So remember the outer loop. We've discussed the inner loop. This inner loop was actually also the idea underlying the item B, but what is now new in the item C, the claim C, is that we use that in order to repeatedly decide the unreachability, right? So in item B, we use n of m to decide with positive guesses the unreachability. And we do that repeatedly. Namely, we decide the unreachability of a vertex W prime in order to verify that we've correctly guessed that W prime is not reachable. It's easy to verify whether the positive guess is correct, that W prime is reachable. But the hard part is now verifying that guessing that W prime is not reachable within m+1 steps, because we don't have the information of n of m+1. Instead, we enumerate all vertices that are reachable within m steps using the previous method and verify that the new vertex is not reachable in one step from these vertices that are reachable within m steps. And thus can verify also that the negative guess was correct. And we increment the counter C prime only for the positive guesses, which we have verified, and we do not increment it for the negative guesses, which we also have verified. And thus at the end of the outer loop, C prime, we can safely make sure and output C prime to be sure that it equals n of n+1. So that after one execution of these two nested loops, we really have computed n of m+1 from n of m. And now surrounding all these two nested loops, there's another loop that climbs from n of 0, which is 1, inductively to n of 2 to the s, which is another exponential loop, right? All these loops have exponentially many iterations, but they use only linear amount of memory. And this also, so that at the end of this outer loop, third nested loop, we have calculated n of 2 to the s. And using that, we can then, using item B, decide the unreachability of a vertex within an arbitrary number of steps. Okay, so yes, that was pretty involved, I agree. And but differently, it was more than earned by Neil Innerman to receive the award. And that already ends our lecture for today. Next time, we're going to talk about Oracle complexity theory, kind of a computational complexity counterpart to the arithmetical hierarchy, which we discussed in computability theory. Thank you very much for your attention, and see you next time.